Hi, welcome back to Waygate Technologies. Dan here for the Krautkrämer CL Go Plus Precision Thickness Gauge. In today's episode, we're going to have a look at the use of delay tip probes with the CL Go. In the first release of the CL Go, we are going to provide full support for what is probably our most popular probe for precision thickness measurement on thin materials, and that probe is our Alpha2-DFR. This is also known as the CLF4. The DFRP, the mini DFR, the K-pens will be in the second release of software for the instrument. The initial release of the CL Go will fully support the Alpha2 DFR. So let's take a look at each of these probes individually. The Alpha2 DFR is also known as the CLF4. The CLF4 was the Hearth version, and the Alpha2 DFR was the Lewistown version. These are ideal for measuring thin materials all the way down to about 7/1000ths of an inch or 0.2 millimeters, and they're limited to about 3/4 of an inch with the short delay tip. We do have a longer delay tip available for measuring thicker materials, but with the standard delay tip, about 3/4 of an inch or so is the thick end of the measurement range. It's a 15 megahertz probe. With the Alpha2 and the other delay tip probes, we use multi-echo measurement. So above about 3.5 millimeters of thickness, we measure from the interface echo, the end of the delay tip, where the sound enters the material, to the first backwall echo, as seen in the right screenshot here. Below 3.5 millimeters, we use the interface gate to establish where the end of the delay tip is, but then we look at backwall multiples and measure from the measure between two adjacent backwall multiples. On very thin material, we may be measuring between, say, the third and fourth backwall multiples. On slightly thicker material, here you can see 97/1000ths of an inch block. We're measuring from the first backwall echo to the second backwall echo. Getting into the probes that will be part of the second release, the mini DFR is a smaller version of the delay tip probe. It's a little bit higher frequency, 20 megahertz. Very small delay tip, 1/8 inch diameter, about 3.2 millimeters. This is primarily intended for measuring things like thin wall tubing. The small delay tip makes it easy to peek up on a tightly curved surface like a small diameter tube, and the higher frequency and the short delay tip make it ideal for measuring thin wall materials. The Alpha2 DFRP, as mentioned before, is primarily aimed at measuring plastic. We use a graphite delay tip to get a good impedance mismatch between the delay tip and the material being measured. It's a higher frequency probe as well at 22 megahertz, generally similar in size and shape overall to the Alpha2 DFR. And finally, we have our K-pen collection. These have tapered delay tips with very small contact areas, as small as 65/1000ths of an inch or 1.7 millimeters. These are designed for getting into tight spaces or tight curvature, or reaching down into pits on the surface of the material being measured. They can be a little bit tricky to hold and get coupled well to the part, but this is an area where the CL Go Plus will really shine with these probes. The large, fast updating A-scan will greatly aid the user in the ability to peek up the K-pen. Again, with the mini DFR, the DFRP for plastics, and the K-pens, those will all be part of the second release. And for the initial release, let's take a close look at the Alpha2 DFR. On our instrument, all we really need to do to get started is to select the Alpha2 DFR or CLF4 from the probes list. And then we can calibrate. and begin our inspection. Now, the calibration is a true one-point calibration. We aren't concerned about probe delay because of using essentially an interface gate to detect the end of the delay tip. So we go straight to our calibration block. In this case, I'm already set up for measuring the 138.138 inch block in my collection. I go back to that block. It gets the data, tells me to remove the probe, and now I'm ready to measure. So just that quick and easily. Notice as I'm taking my measurements, here's the 0.138 inch block. That's 3.5 millimeters more or less. And notice that my measurement carats at the top of the A scan, I have 3 carats showing. The green, going with the interface gate, shows me where it's taking the edge of the interface echo. And blue is the zero cross from the first backwall multiple, and red is the zero cross from the second backwall multiple. My thickness measurement is being taken between the first and second backwalls. If I go to a thicker step, now I'm above 3.5 millimeters. This one is about 4 millimeters. And notice now I no longer have the red caret on the screen. My thickness measurement is being taken from the interface echo to the first backwall. So once we get into thicker materials, that's going to be the measurement mode in each case. So again, the threshold is a little bit above 3.5 millimeters. Thicker than that, we use interface to first, and thinner than that, we're looking at first to second, or as we go thinner and thinner yet, we will start to see where we're looking at the third and fourth backwall multiples. So here we're getting thin enough that the first backwall echo is getting very close to our interface, and rather than risk the possibility of the signal being distorted by recovery from the interface echo, now we're taking our measurements from the second to the third backwall multiple. Go a little bit thicker. Here we're still doing second to third. And by the time we get to (79 thousandths) roughly, about 2 millimeters. Now, because of where our gates are positioned, we're measuring first backwall to second. Okay. We can look at increasingly thin materials here. Here we're down to 19 thousandths, so roughly 0.5 millimeter. Now we see we're picking up the, looks like the third to fourth backwall multiples, but we're still able to measure quite nicely. Here is 10 thousandths, just a bit more than 1/4 millimeter. And we see that our echoes are beginning to run together pretty well, but we're still able to tease the reading out of that. If I go to the measure menu and reduce my display range, now I can see better what's going on there. We can measure down to 7 thousandths of an inch well with this. We still have a set of echoes that look similar to that at 7,000. At 6,000, the cycles of sound overlap so much that they begin to cancel each other out. And it's not so much a shortcoming of the instrument, it's just the fundamental frequency of the probe and the behavior of the sound waves. This is all that we see on a 5 thousandths thick piece of steel. At 10, we have a nice pattern like this that we can work from. We have that down to about 7 thousandths. From 6 thousandths of an inch and thinner, the cycles of the sound pulse are canceling each other out, and we're left with no signal to be able to take a measurement. So that's it for the delay tip probes, for the Alpha2-DFR probe in particular. Thank you for joining me today. As always, if you have any technical questions, please reach out to remote service at bakerhughes.com. And if you're interested in seeing a demo or getting a quote, please contact your local Waygate sales engineer or your local channel partner. Thank you for joining me, and until the next episode, this is Dan for Krautkrämer CL Go Plus.